Laplace transform using the definition for this function cosh bt. We know that Laplace of any function, let's say of t, when we take Laplace, the definition is just improper integral 0 through infinity. Here we get kernel e raised to negative st times the function itself, and we evaluate dt. And at the end of the day, when we evaluate, this is gonna be a function, let's say uppercase f of variable this. Okay, our function here is now ft, and we are asked to use this definition. So let's do it. And Laplace of the given function is improper integral 0 through infinity of kernel e raised to negative st of the times the function cosh or cosine hyperbolic bt dt. Now we can do a little bit of background work so that we can kind of cheat in this question, because we know cosh of some angle is just half of e to the that angle plus e to the negative of that angle. So I'm going to write cosh bt in this way using this definition. So that gives 0 through infinity of e to the negative st times 1/2 e to the angle, that's bt, plus e to the negative angle bt of dt. Okay, now we got 1/2 can be pulled all the way outside. This is an improper integral because we are working on 0 through infinity, so we need to work on 0 through some finite number, let's say a, and we let that a eventually go infinity, and 1/2, and we can just distribute inside there. Okay, so that is in fact, let me put bracket, e raised to, when we multiply we add the exponents, so that's going to be negative s minus bt. This is negative st plus bt. I kind of manipulated, I took negative and t out, that leaves s minus b. Okay, so similarly for the second, when we distribute here, plus e raised to negative s plus bt. Okay, when we multiply this, and we need to work on this integral. This 1/2 can be pulled all the way outside, and we got limit a going to infinity. Now we can find the antiderivative of these two functions. We know that when we have e raised to negative, let's say negative or positive, doesn't matter, alpha of some variable alpha x, and if you want to integrate with respect to x, it's going to be same thing, exponential function, and we need to divide by alpha. In fact, this is a small application of U substitution, so I'm going to apply this rule where alpha is negative s minus b here, and here is s plus b. Okay, so this one I'm going to integrate. That means this integral sign is gone, so this is same thing, s minus bt divided by this coefficient s minus b. Remember, our variable is t, so t is the variable, and whatever else counts as constant, so we need to divide by that, plus same thing here, e raised to negative s plus bt divided by this s plus b. And now we need to evaluate this integral from our limits 0 to a, so this is going to be 0 to a. Okay, let's evaluate this. So 1/2 limit a tends to infinity of let's replace t by, because t is the variable, upper limit a and t 0. Okay, sometimes we write this just to see what we are replacing. by, so upper limit a means e raised to negative s minus b times a all over negative s minus b. That's still upper limit e raised to negative s plus b, okay, times a all over minus s plus b. That is when we plug in upper limit a. Okay, that's upper limit minus lower limit means t equals 0. So 0 means e raised to 0. E raised to 0 is 1. Okay, 0 makes this thing 0. E raised to 0 is 1. So 1 over minus s minus b plus sign t equals 0 makes this whole exponent 0. E raised to 0 is 1. So 1 over negative s plus b. Okay, that is what when we plug in. Now we need to take the limit when a goes to infinity. Let me remind you of something. When we have e raised to, let's say, some number x, and when x goes to negative infinity, this is 0. Or if this is negative and x goes to let's say positive infinity, the same thing. Okay, this is pretty much the graph of e to the negative x, and when x goes to infinity, the graph becomes pretty much asymptotic to x-axis. So I'm going to apply this rule. E to the negative infinity is 0 when we plug in that. Okay, so a is going to infinity, so this is going to go to infinity. So as long as this is positive, s minus b positive, so s minus b positive means s must be bigger than b. So if s is bigger than b, then this is positive, a is going to infinity, so negative infinity. So this is gonna go to 0 provided s minus b is positive, because this positive means the whole thing becomes negative, and e to the negative infinity is 0. Similarly here, this is gonna go to 0. Okay, let me move this away. When s plus b is positive, because this is positive, a is going to infinity, the whole thing goes to negative infinity. So here we need the restriction of s plus b positive, means s is bigger than negative b. Okay, s plus b must be positive so that the whole thing is positive, so negative infinity. That means s is bigger than negative b. So these are two restrictions. So s is bigger than b, s is also bigger than negative b. So here, so this is whole thing is 0 now, because 0 over some number is 0, 0 over number 0, so we are left with that. So 1/2, I just took the limit, there is no a, uppercase a, so there is nothing to do here. So negative, now I can distribute this negative sign, this negative makes this negative positive, so 1 over s minus b, okay, and here is negative, negative again positive, 1 over s plus b. Now we need to combine. Here we got s is bigger than b, and s is bigger than negative b here. S plus b positive means, yeah, that's the case here, which is same as absolutely s is bigger than b. Okay, I think that works, and this is not really important. You can just ignore that part now. Now let's work on this. So half, when we combine this one, is now s square minus b square, common denominator, s plus b plus s minus b, that is 1/2, b cancelled, 2s over s square minus b square, 2 and 2 cancel, so s over s square minus b square with correct restriction. So this is the Laplace transform of cosine hyperbolic bt, final.